Alright, so today we're going to have a look at the remainder theorem. We'll have a look at another theorem, the factor theorem, later, but today we're going to have a look at the remainder theorem, how to prove it and how to use it. So the remainder theorem is that when we divide a polynomial, p of x, that's our polynomial, when we divide it by a linear term, x minus k, until there is a constant remainder r, then we can say that remainder r could have been found if you just put the k that we were dividing by into the p of x. So the remainder equals p of k. All right. You might not believe me, but let's have a quick proof of that. So the first thing is that we know that by the division algorithm, so this is what we got earlier. By the division algorithm, we know that p of x is equal to the q of x, the quotient, times by x minus k plus r, the remainder. All right, so we know that already. Well, let's say we're going to let x equal k. All right, so we're going to change all our x's into k. So basically what we get is p of k equals q of k times by k minus k. We're changing all of those x's plus r. All right, so that means p of k, that's going to stay the same, equals q of k. We can't change that. But what we do see is k minus k equals 0. So this is going to become times by 0 plus r. All right, anything times by 0 is just going to go to 0. It's going to go away. We're left with p of k equals r. All right, so the remainder is something we had to find out by using division, but using the remainder theorem, we see that if we put in k, and k, remember, is that term we're dividing by, that constant term in that linear function. If we put that in, we'll end up with just the remainder, and that's the remainder theorem. All right, so let's have a look at an example of how to use this. So use the remainder theorem to find the remainder when this polynomial to degree 4 is divided by x plus 2. All right, so I guess the only tricky thing that we have to keep our eye on is this function that we're dividing by is always written as x minus k. All right, so we've got to change the sign for that k. So here we've got x plus 2. So we could rewrite that. It's a good way to think of it as x, because we want to write minus k, so you'd write minus, but to keep that constant, you'd have to write minus 2. So that is our k, is negative 2. All right, so let's call p of x, let's call that x to the power of 4, take 3x cubed, take x, take 4. So if I put in my k now, so p of negative 2, that should give me my remainder, all right, which is negative 2 to the power of 4. Again, we want to do that in brackets, so we don't lose any or gain any negatives. Minus 3 of negative 2 cubed, take negative 2 minus 4. Okay, so 2 times 2 is 4, times 2 is 8, times 2 is 16, and that's going to be a positive 16 for this first one. 16, subtract 3 times by negative 3 times by 2 cubed is going to give us negative 8. Subtract negative 2 is going to become plus 2 minus 4. All right, so simplify this, we're going to get 16. Negative 3 times negative 8 is positive 24. Plus 2, take 4. And you get 16 plus 24 is 40. Plus 2 is 42. Take 4 is 38. So this equals 38. So as per usual, we're going to finish this off with a sentence. So when x to the power of 4, take 3x cubed, take x, take 4, is divided by x plus 2, the remainder, and we call that R, is 38. Okay, so it's nice to write that in a big sentence, and then what you'll do is also in these funny squiggle brackets that we've used before is we'll write remainder theorem. All right, if I just move my head out of the way there. Remainder theorem, because that's the reason we were able to say that. All right, that's telling someone that's looking at your work how you came to that conclusion. All right, so that's the first little example. All right, so let's have a look at a bit more of an elaborate example. So we've got p of x, when p of x is divided by a quadratic this time, x squared minus 3x plus 7. The quotient is x squared plus x take 1, and the remainder is rx is unknown. Okay, so when we divide it by that, it's unknown. When p of x is divided by x minus 2, the remainder is 29, and when p of x is divided by x plus 1, the remainder is negative 16. And what we've been asked to do is find r of x in the form of a plus b. The first thing we're going to do is we're going to write out using the first bit of information that we've got. So what we're going to do is our p of x equals our quotient, q of x, times by our divisor, d of x, plus our remainder. All right. Now, given what we've got at the top, we can write this as the quotient is x squared plus x minus 1. So that's our quotient. And the divisor is x squared minus 3x plus 7. Okay, because we're in the form of a quadratic, our remainder is going to be in the form of a linear, so we can write that as ax plus b. Now the good thing about the remainder theorem is that we can use what we've got in this second part to work out these unknowns, right, and work out the remainder, and that's exactly what we're going to do. So what we do know is from this here, when our k equals 2, so when we've got p of 2, we get a remainder of 29, okay, and that's using the remainder theorem. Ooh, lost my eye, remainder theorem. Okay, so if I chuck my 2 into here, I'm going to get 2 squared plus 2 take 1 times by 2 squared take 3 lots of 2 plus 7 plus a times by 2 plus b, and that's going to equal 29. All right, so I'm going to quickly sum those up. All right, so if you quickly multiply these numbers out, you'll get 25 plus 2a plus b equals 29. Okay, so if I just move my 25 to the other side, I get 2a plus b equals 25 minus that from both sides, I get equals 4. All right, and that's my first useful term. I've got 2 unknowns in one equation, so I can't work it out, but we have enough to do it again. So I'm just going to save that up here. So 2a plus b equals 4, and that's our first equation we're going to use. All right, so we're going to do the same thing again. So originally we had x when x minus 2, and the remainder was 29. So now our k is negative 1. All right, so we've got to have, so when we have p of negative 1, we get, substitute negative 1 in here, so negative 1 squared plus negative 1 take 1, all times by negative 1 squared take 3 times by negative 1 plus 7 plus a times by negative 1 plus b. So again, I'll quickly compute that, but all of that equals to negative 16. So this equals negative 16. So that's going to be equal to, where's my pen? There it is. equal to, what's happened, -1 times by 11. Take A plus B equals -16. All right, so therefore -A plus B equals, move that to the other side, we get -5. All right, so now we've got our second equation, our first one. So if we solve these simultaneously, all right, what we get is, let's say we can do this heaps of ways, so let's just call this equation 1 and equation 2. All right, let's just do 1 minus 2, which equals 2a minus -a, which is going to be 3a. b minus b is 0. 4 minus -5 is 9, so 3a equals 9. So therefore a equals 3. Now we can substitute that 3 into either one of our equations. So let's put it in this number 2. So put this into equation 2. We get -3 plus b equals -5. So b equals -2. Okay, so therefore r of x, so our original question was find r of x in the form of ax plus b. R of x equals, our a is 3, so 3x plus -2. So you can just write negative minus 2. Okay, excellent. And we've been able to do that using the remainder theorem. So we'll have a go at a couple of these now, but thank you.